Here we are, 6.6 part 2, the solving of exponential equations. There's a theorem out there, and it's called the property of equality for exponential functions. It says if b is a positive number other than 1, then something must be true. So if you have a base to the x, and you have the same, and that's the key, they are the same base to the y. So if this is true, then x must equal y. And it's a common sense theorem that turns into something much more difficult. But here's an example. If 3 to the x is 3 to the 7th, then x must equal 7. Because this would result in 3 to the 7th equal to 3 to the 7th. So that's an easy one. It's not going to be that easy, though, because to do this means you have to have some number sense. You have to have number sense to do these things. You have to be able to look at a number and think about its powers that make it. Like 8. 8 is 8 to the first. Or it's also 2 cubed. Or, this will blow your mind, it's also a half to the negative third. Now, how did Milbrath know that? Because the negative number flips it, and 2 cubed is 8. So you have to be willing to go outside your comfort limits, and you have to think about different ways of writing numbers. Not everybody can do that, so it's kind of a hard section for some. 9 is a power of 9. It's 9 to the first, or it's 3 squared, or maybe it's 1 over 3 to the negative second. Lots of ways of writing a 9. I know you may not believe me, like that's a foreign language to you, but I'm not wrong about this. 64 could be something like 8 squared, which means it could also be 1/8 to the negative second. It could be 4 cubed, or it could be 1 over 4 to the negative third, or it could be 2 to the 5th. Yeah, 2 to the 6th. 4 to the 16, yeah, 2 to the 6th. Or it could be something like a half to the negative 6th power. Lots of ways you can rewrite numbers. Speaking of these fractions, fractions can be written as whole numbers if you rewrite the exponent. I know you're like, Milbrath, that doesn't seem right. We studied exponent rules. We studied negative exponents. You take 2, you raise it to the negative first power, you get a half all day long. A fourth could be 4 to the negative 1, or it could be something like 2 to the negative second. And again, you might have to be willing to push some buttons to figure some of this out, but that's 0.25, which I know not everybody knows, because whatever, is a quarter. All right, so here we are on the solving things. So we're going to solve this, and we're going to use the property b to the y, x equals b to the y, but these must be the same base. Right now, the bases are not the same, but I can make them the same. 81 is 9 squared. So I'm going to rewrite 81 as 9 squared, and I'm going to keep the exponential space, which was 3 minus x. One more. 1/9 is 9 to the negative first, but I'm going to keep the exponential space there. Now, once the bases are solved, I remember actually teaching some of this back in geometry way back upon time. I don't know why it came up, but we did it. And kids didn't have a problem with that. Now, that would have been 2013. If you can get the bases the same, chunk them. All right? As soon as the bases are the same, you can chunk them. We're going to invoke the distributive property. That's going to be 6 minus twice x equals negative 5x plus 6. And then we're going to get our x's on one side and our numbers on the other. I'm going to shift 5x over here, and I'm going to shift 6 over there. So I'll have 5x minus 2x equal to 6 minus 6, because if you jump equality, you change your sign, blah, blah, blah. 3x is 0. Divide by 3, and oddly enough, I did a lot of work to get nothing back. X is 0 is a correct answer. Who would have thought? It is too, by the way. Because if you make that a 0, then that's gone. 81 cubed is a gigantic number. You get that. Let's see what 1/9 to the -6 power is. And by gosh, they're the same thing. All right, moving forward. 1/2, remember I told you 1/2 could be thought of as 2 to the -1st. And that's how I'm going to do it. I'm going to make a desired base to be a 2. It's the easiest way to show it. 16 is 2 to the 4th. And now I have the bases the same. Get rid of the things, okay? Just chunk them. I'm going to go ahead and invoke the distributive property as I set things equal to -3x plus 2, and I know I shouldn't do this because some of you all will be confused because you don't know how to do basic math, equals 4x plus 12. And then we're going to put our x's on one side and our numbers on the other. So we're going to shift that over, make that a 7x. 2 minus 12 is -10. Divide out the 7. X is -10/7. It's a funny answer. It's not even a nice answer, but whatever. Moving on to C. If I saw a 4, I would choose 2 to be my base. 2 to the 2 squared times the existing x. And if I see a half, I make it a -1 to the x minus 3. So if you thought you didn't like exponents before, you probably really don't like exponents now. Anyways, I know that 2x must equal -1 times x minus 3 because the bases are the same. And I know the distributive property, so -1 times x is -x plus 3. And I'm going to add an x and get a 3x. 3x is 3, and by gosh, x is 1. So I don't think those are bad, but I'm good with numbers. Most of you are not. It's going to kind of stink. I'm sorry. All right, now, then you run into these questions that even I can't solve. Like this question says, what power of 7 is 15? Don't have a clue. I do know that 7 to the 1st is 7 and 7 squared is 49, so I know that x is somewhere between 1 and 2. I know that much, but that's all I really know. I could make a guess. I might even be pretty close based on experience. So what we do is we do our logarithms. We have a base, we have an exponent, and we have an argument. So remember, log is bay. Some of you guys still have not had that click yet. A logarithm base b argument a equal to e is equivalent or has an equivalent inverse of b to the e equals a. So let's do the conversion. Log base 7 of 15 is equal to x. Now, how does that help me solve? That helps me solve because I know change of base. I know that a logarithm of base b argument a is equal to, and I like ln a over ln b. There's a reason I like ln. You'll see in just a few minutes why I like ln. Anywho, this piece could become ln 15 over ln 7, and that is my answer, and it makes sense to go ahead and push some buttons and see what she is. ln 15 divided by ln 7 is roughly 1.3917. All right, and here you guys have already been doing this, so like we're really just reviewing and introducing something new and reviewing and introducing something new. You'll get logarithms by the time I'm done with them. Remember, we do easy stuff first. And by the way, I have no idea e to what power times 4 minus 7 is 13 is. We're going to add 7 and get a 20. We'll have this line right here. Hopefully the kids that are doing this, that need to be doing this, are doing this. And then we have e to the negative 0.3x equals 5. Log is bay. Log is bay. Base. Exponent. Don't be the kid who can't identify an exponent. Bases have exponents. Argument. Log base e argument 5 is equal to negative, I'm going to rewrite this as -3/10 of x because I feel special. All right. Log base e is known as ln. And the opposite of division is multiplication, so I'm actually going to multiply both sides by 10 at the same time. Cancel, cancel. And then I'm going to divide by 3. And it was a negative 3. There you go. Negative 10 natural logs of 5 over 3 is your answer, and it is as pretty as it's going to get. So negative 10 ln's of 5 sitting pretty over a 3 is the correct answer. It's about negative 0.53648. Here's another technique, and it's a really good technique. It works well for kids who struggle with log is bay. So I'm going to put a little note here. If you struggle with log is bay, this is for you, because it is for you. And the technique is called ln both sides, and you can also do a technique called log both sides, because as long as you do the same thing to both sides, the property of equality is true, but it still requires isolation. You still got to do all the easy stuff first. All the techniques require isolation. So I added 4 to 20, got 24. Now I'm going to divide the 3 out, and I'm going to get an 8. And that's where I'm at. So now I'm going to hit it with this technique of ln'ing both sides. I'm going to ln the left, and I'm going to ln the right. Now, using this property still requires you to understand that a logarithm of argument a with an exponent of r is r log a. You still have to know that. You're going to take that 3x and you're going to put it out front. 3x, natural logs of 4, is the natural log of 8. Keep playing your isolation game. Both of these pieces were being multiplied by x, so the opposite of multiplication is still division. You divide both sides by 3 natural logs of 4. There's your answer. It is one of my favorite techniques with logarithms. 99 out of 100 times, it is the easiest way to do a problem, and I mean that. I don't even know if I get to show you anything in Algebra 2 where it's not one of those cases, but 99 in 100 times, it's the easiest way to solve a log. It really, really is. So if log is bay is a struggle, this is your winner chicken dinner. And this is the you try, please try. You gotta try, man. And that's it for your notes on Monday.